So this molecule has two chiral centers, 1, 2, and this whole group is the third group. So this carbon, though bonded to the double bond, but the valency is fulfilling and satisfying itself. So these two are the chiral carbons. So we will call it the asymmetric carbons atoms. So these are the examples of chirality centers with the examples of the stereo centers. So these are also called the stereo centers. Now the achiral compound, when the images can be superimposed, the compound is achiral. Okay, so understand from this example, like this is the carbon and these two groups are 3 3, these are same 2 1, and we will rotate it to the 180 degree. So if we rotate it to the 180 degree and pick it up and impose onto this one, then they will be superimposed. So these will not be the enantiomers. So this is just the very simplest concept, that this is the achiral molecule. And now the plane of symmetry. So plane of symmetry is another indication that the carbon is not chiral, because the plane is passing within the molecule. So a molecule that has a plane of symmetry is also achiral. Let's see, we will divide this molecule into this. These two sides would be the same. And if we divide this molecule like this, if we cut the molecule in this direction, like horizontally, then the back side of the half and the front side of the heart would be same to each other, and would be the there would be the presence of the plane of symmetry, and the molecule would be achiral. Now about the cis cyclic compounds. So a cis cyclic compound is basically achiral, because if we have the two carbons, let's see this and this, and although they are the chiral centers, but a plane of symmetry is passing through it, and these two sides are equivalent to each other and they are similar. So the overall the whole molecule would be achiral. Although these two are chiral centers, but the plane of symmetry is passing, so the whole molecule would be achiral. So this is the example of cis 1,2 dichlorocyclohexane is achiral, because the molecule has an internal plane of symmetry. So this is another indication and symbol of this, that the molecule is achiral. And about the trans, if we apply the formula of the plane of symmetry, and we will cut the molecule into this half and into this half, then we'll see that these two sides of the groups are not similar to each other, they are different. So we will call it the chiral molecule. So trans 1,2 dichlorocyclohexane does not have a plane of symmetry, so the images are non-superimposable, and the molecule will have two enantiomers. And what we have discussed, that if there is a presence of the chiral center, absence of the plane of symmetry, and non-superimposable images of each other, then the two molecules would be enantiomers. First of all, what? The presence of the chiral centers. Chiral center means the four different groups are attached, and there is no plane of symmetry, like we cut the molecule into two halves, they would not be similar to each other. And the third one is that they are non-superimposable. If we rotate the molecule to 180 degree, and then we will pick the reflection or the other molecule, and we will try to impose it the first one, then they would be non-superimposable. So this is the example of the transcyclic compounds, and basically the trans are the chiral and cis are the achiral. So there is another topic about the RS and S configuration, like how we will name the enantiomers, what is R and what is S. So there are some kind of rules. We will call the Chan in Gold-Free law convention. So enantiomers have different spatial arrangements of the four groups attached to the asymmetric carbon. The two possible spatial arrangements will call the configurations. Okay, the arrangement of the groups that are attached to the carbon have different arrangements in space, and each asymmetric carbon atom is assigned a letter R or S based on its three-dimensional configuration. They would be three-dimensional, and what they will have an orientation and configuration of the groups we will assign according to the R and S. According to that orientation, what molecule would be the R and what molecule would be the S. So we will call this nomenclature the Chan in Gold-Free law convention is the most widely accepted system for naming the configurations of the chirality centers. So first rule is that assign a relative priority to each group bonded to the asymmetric carbon. For example, iodine has the most largest atomic formula. And then the bromine, chlorine and sulfur, and fluorine has 9, oxygen has 8, nitrogen has 7. So according to their atomic number, we will assign the priority. For example, let's see, this is the chiral carbon and 4 different groups are attached to it. How we'll assign the first priority group? According to their atomic number. So fluorine has the highest atomic number and we will assign it 1. Fluorine has 9 atomic number, nitrogen has 7, carbon has 6, hydrogen had 1. So 1, 2, we will not see the secondary attachment, we will see the primary attachments. The primary attachment is fluorine, the primary attachment is nitrogen, the primary attachment is carbon, the primary attachment is hydrogen. The secondary attachment is the further 2 hydrogen molecules are attached to the nitrogen atom. We will see it later. First we will see the atomic number of the primary attachment. So 1, 2, 3, 4. So we will assign the numbering, and same is the case with that. In case of ties or the secondary attachment, use the next atoms along the chain of the each group as tiebreakers. For example, we have the same 2 attachments. How we will assign it? Then we will